Let's look now at one of the appendices, Appendix A.2 on mathematical induction. So what we'll do in this section is we'll introduce and define math induction, and we'll apply it to several of the formulas we've encountered to date, date being somewhere around section 5.2. This would be good supplemental reading for section 5.2. Where we started using the sigma notation and limits of finite sums. And there's some summation formulas that are stated in that section without justification. You need math induction to justify them. So in this appendix, we'll state the mathematical induction principle, as the book calls it, and use it to give proofs of some of these results we've used, in particular related to the summations of the first n natural numbers, summations of the squares and the cubes of the first n natural numbers. We'll establish those formulas rigorously in this section. Okay. The induction principle really comes out of the area of math called set theory. I have a bit of a discussion of this in some notes I prepared for discrete math. A link is given in the notes posted online there. This discrete math class no longer exists at ETSU. We have math reasoning, Math 3000, that would cover these topics as well. I don't have notes online for that just yet. But math induction is usually covered in a sophomore, junior level class. So doing it in Calculus 1, well, it comes in supplementally. All right, here's a statement of the induction principle. It's really part of the definition, the very definition of the natural numbers. And it states, let P of X be a property, possibly with parameters, more on that shortly. Assume that P of 0 holds, that is, the property holds for 0, and for all n a natural number, when P of n holds, that implies that P of n plus 1 holds. P of n, the truth of P of n implies the truth of P of n plus 1, the truth of that property. That property for us will usually be formulas. The claim is, then this property P holds for all natural numbers. I also have some notes online for set theory. ETSU sadly doesn't have a formal set theory class. If you'll follow the link to those notes, section 3.2 has properties of the natural numbers and elaborates on this a little bit. Now this is stated in Thomas's calculus as follows. First, it's called the mathematical induction principle. Mathematical induction is a title of this appendix. And the property mentioned above is really formulas. So Thomas states this in terms of formulas. It could be something a little more involved than a formula. It could be claiming the existence of certain mathematical structures involving parameter n. So it could be more involved than a formula. We only need it to deal with establishing certain formulas. So in connection with establishing a formula, when formulas are, in a sense, functions of a natural number, so this is the proposition, then Thomas states that the technique of proof by induction requires 2 steps. Check that the formula holds for n equals 1. Prove that if the formula holds for any natural number n equals k, then it holds, there's the if then, for the next natural number, n equals k plus 1. From that, you can conclude that the formula holds for all natural numbers n. So to link together Thomas's version with that version mentioned above, the property P mentioned above is the same as formula used by Thomas in this appendix. So the idea is establish the formula for n equals 1. Assume the formula for n equals k, and show that implies that the formula holds for n equals k plus 1, the next natural number. And we'll use this notation and go through several examples that specifically follows this. I want to think of this kind of like knocking over dominoes. If we have a long linear arrangement of dominoes, nothing elaborate, just a straight line distribution of dominoes, we want to knock all the dominoes down. You could do so if you knock down the first domino, that's establishing the formula for n equals 1, and then you make sure that whenever a domino falls, it knocks down the next domino. Slightly more symbolically, in terms of the symbols we had above, we get the following. Borrowed these from mathcool.com, these images. So you're going to show that the first domino falls, then you're going to assume the kth domino falls and show that it knocks down the k plus first domino. From there, you can conclude that all the dominoes fall. You know you knock down the first one, and you know whenever one falls, it knocks down the next one. So the first one knocks down the second one knocks down the third one, and so forth. So the ideas behind this are actually that elementary. So let's go through several examples. So we'll illustrate this in connection first with those formulas from section 5.2. Example A.2.1, I've stated it as, so numbered it. Use math induction to prove that for any natural number n, the sum of the first n integers, here it is written in the sigma notation, with I as the index, I usually use k as the index, but we're going to use k for something else. So I've changed the indices, they're dummy variables, but with I as the index, sum from I equals 1 to n of I is n times n plus 1 over 2. We used that when we first encountered definite integrals and approximating definite integrals. So let's go through a proof of that using induction. All right, there's a claim and the induction procedure, and we'll speed this up because we've got lots of examples put in the notes here, and it's always the same procedure. We'll check it for n equals 1. We plug in n equals 1, that would be the sum from I equals 1 to 1 of I, that'd be 1 plus nothing else, and you plug n equals 1 into the formula, you get 1 times 1 plus 1 over 2, 1 times 1 plus 1 over 2, which also equals 1, is true. So the formula holds when n equals 1. That's step 1 of math induction. Step 2 is to assume the formula holds for n equals k. That is the sum from 1 to k, the sum from I equals 1 to k of I, equivalently, equals k times k plus 1 over 2. So we've plugged n equals k into both sides of this equation, and we're assuming that that holds. Now we want to see what happens when n equals k plus 1. We want to show that the formula holds when n equals k plus 1. So we'll add 1, 2, up through k plus k plus 1. And I want to take that summation and associate the first k and have the next one, the k plus 1 term, pulled over to the side. Because I know what the sum for 1 through k is. That's the induction hypothesis. So here's the plan. We've shifted from summing 1 through k to summing 1 through k plus 1. So this is showing the kth domino knocks over the k plus first domino. Here's the falling of the kth domino, assuming the formula holds for n equals k. And we're working on showing the formula also holds for n equals k plus 1. That is, the k plus 1 domino falls. So here's where we left off. We've got the sum of 1 through k plus a new term, think of it as. We've assumed that the formula holds for summing 1 through k of I. So rewriting the sum from 1 through k as in the summation notation. We've assumed that is k times k plus 1 over 2. That was the induction hypothesis. We said if the formula holds for n equals k, well, that's exactly what you have here, the case n equals k. So there's the induction hypothesis being used. We just need to add on this extra term. Let's get a common denominator. This has a denominator of 2, so let's give this one a denominator of 2, multiplying by 2 over 2. Common denominator, we can add the numerators together. Let's see, we can factor a k plus 1 out, leaving you with a k plus 2 in the numerator. So this is what that produces. Let me rewrite this in the following form. Remember where we're going. K plus 1, k plus 1, k plus 2. Let's write k plus 2 as the quantity k plus 1 plus 1. There I've got a k plus 1. There I've got a k plus 1. If we let n equal k plus 1, then it can be rewritten as n times n plus 1 over 2. And the result holds for k plus 1. The sum from 1 to k plus 1 is of that same form, where n equals k plus 1. So this shows that the k plus first domino falls on the assumption that the kth domino falls. So the formula works. For n equals k plus 1, I very explicitly made that substitution, and math induction tells you that this formula holds for all natural numbers. So there's a proof of that, and we got several more of those formulas from that section. Thomas makes a comment. You don't need to start at 1. We could start at any natural number, call it n sub 1. And then if we apply the principle of induction, show the formula holds for n sub 1, some natural number, some integer even. And we show that if the formula holds for k, then it holds for k plus 1. Then we can conclude that this formula holds for all n greater than or equal to n sub 1. You don't have to start at 1. You could start at any integer and follow the same procedure. And then you would establish the formula for any integer greater than or equal to that place where you started. Well, with what we'll do, we'll start with 1 in all of these examples. Here is a generalization of the derivative sum formula. Back when we were taking derivatives in chapter 3, was theorem 3.3.E. We had actually used this without ever explicitly saying so, which I got no regrets on that. It says, and it might even come to you as a surprise that we even need to establish this, but let's illustrate math induction by establishing this. Certainly you believe it to be true, given that it holds for the derivative sum rule for sum of two functions. Suppose u1 through u sub n are differentiable functions, then the derivative of the sum is the sum of the derivatives. Technically, when we did the derivative sum rule, we only had 2 functions. We didn't have just a whole collection of functions. We only had 2. So arguably, this needs to be established. It's not surprising. We've already used it. Well, what a fine opportunity to illustrate the principle of mathematical induction. Okay, so we want to show the derivative of a sum is the sum of the derivatives when that sum involves more than 2 things. When n equals 1, this would say the derivative of u sub 1 equals the derivative of u sub 1, which is true. Let's go a little further than that. Let's show this also. This is not technically necessary to establish the proof, but I think it's slightly enlightening. Let's show this holds for a sum of 2 functions. Actually, we'll use this in the proof here shortly on the next slide. If we want to take the derivative of u1 plus u2, does that equal the derivative of u1 plus the derivative of u2? Well, actually, that's exactly what the sum rule states. And we went through back when in section 3.3 a proof of that, probably with the limit definition of derivatives. So the result also holds for n equals 2. So we've shown it holds for n equals 1 and 2. Arguably, this is not necessarily needed. We're going to use it down below. So that's the reason I mention it. And we already had that established from the derivative sum rule. So secondly, the induction stuff. Assume the formula holds for n equals k. So when we add k functions together, the derivative of the sum of k functions is the sum of the derivatives of those k functions. N equals k, k functions. We want to show the result holds for n equals k plus 1. Suppose you add together k plus 1 functions and differentiate. By the way, let's take that sum of k plus 1 functions and use associativity properties of real numbers and associate the first k functions, and then treat this one as like the next one added on, like we did above. I know how to differentiate a sum of 2 functions, and we got a sum of 2 functions here. That's why we did the n equals 2k separately. Okay, so we left off with these associated. So I want to treat this as a sum of 2 functions. This is the first function in parentheses. This is a second function. Well, the derivative of a sum of 2 functions is the sum of the derivatives. That's the derivative sum rule. So we'll take a derivative of that first function plus the derivative of that second function. Oh, but when we take the derivative of u1 through u sub k, we assumed, this is the induction hypothesis, that that's the sum of the derivatives. So we get the sum of the derivatives there. Differentiate u sub k plus 1, differentiate u sub k plus 1, just alternative notation for the derivative. So by the induction hypothesis, we get the sum of these derivatives. We had tacked on the right the derivative of that k plus first function. That's a sum from 1 to k plus 1 of the derivatives of the u sub i's. That is, its derivative of the first plus the second up through the k plus first one. Say up through the nth one, where n equals k plus 1. We assumed on the previous slide that the formula held for n equals k. That is, we assumed exactly this. And we've now shown that the formula holds for n equals k plus 1. Differentiate k plus 1 functions, you get the sum of those k plus 1 derivatives. Result holds for k plus 1. So by math induction, it holds for all natural numbers. Okay, let's see. We got just more examples. Yeah, so the rest of it's examples. So let's just go through the supplemental file and just do more of the same. So this will get boringly repetitious. I'll speed it a little bit of it up. It's always the same procedure. Check for n equals 1, assume for n equals k, and show formulas hold for n equals k plus 1. Here, this is one of the exercises from the appendix. See, this will be useful when you encounter geometric series, something you'll see in calculus 2. This is not a series, this is a finite sum, because we haven't done series yet. So it's proved that if r is not 1, then 1 plus r squared, blah, 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 up through r to the n equals 1 minus r to the n plus 1 over 1 minus r for every natural number n. All right. First, we'll check the formula for n equals 1. N equals 1, we'd have 1 plus r. On the left-hand side, over here, we'd have 1 minus r to the 1 plus 1, 1 minus r squared over 1 minus r, 1 minus r squared over 1 minus r. 1 minus r squared factors into 1 minus r times 1 plus r. Can you cancel those 1 minus r's? Yeah, as long as r isn't 1, and it isn't. So we're good to go on that. And we get 1 plus r out of the right-hand side formula. And in fact, that's true. 1 plus r equals 1 plus r. Next, assume the formula holds for n equals k. So we'll assume the sum from 1 to r to the k, the powers of r, is 1 minus r to the, see, I'm plugging in n equals k, r equals k plus 1 over 1 minus r. We simply replace the n with a k. We didn't do a k plus 1 thing. The plus 1 comes from up here in the formula. All right, so we just substituted in n equals k. We want to show the formula holds for n equals k plus 1. So add the next term, 1 through r to the k plus r to the k plus 1. So add the next power of r. Let's associate the first k terms. So you should know where we're going by now, because we've already done the same type of thing twice. And then treat this as a new term. Next slide, I'll say, well, I know what that is. We just assumed the formula holds for that. So I'll replace the sum of the first k with this term here. We'll get a common denominator. And if the formula is true, things will work out. And the formula is true. Okay, so let's see, we left off with this summation here. We had assumed that the sum from 1 through r to the k was given by the formula when n equals k. This is exactly what we had on the previous slide. Add the next term. There's the use of the induction hypothesis. Let's get a common denominator. So it looks like it'll be 1 minus r. So let's take this, multiply by 1 minus r over 1 minus r, giving us a common denominator. Add the numerators, 1 minus r to the k plus 1. There you go. This thing, let's distribute. That'd be r to the k plus 1 minus r to the k plus 2. Yeah. Distribute. Use the common denominator, adding the numerators together. And look at this. Those two terms cancel. Negative r to the k plus 1 plus r to the k plus 1. We've lost that. We're left with 1 minus r to the k plus 2 in the numerator, 1 minus r in the denominator. Remember where we're going? If I treat k plus 2 as k plus 1 and let n equal k plus 1, that exponent becomes n plus 1. And we get we get 1 minus r to the n plus 1 divided by 1 minus r. And that is the formula with n equals k plus 1. So the result holds for n equals k plus 1. By math induction, it holds for all natural numbers n. This might also arise in dealing with some geometric things in probability and statistics. These might represent, probabilities of certain types of events. Anyhow, you're very prone to encounter this again, which is why I included it in this supplement. Here's something we've used in section 5.2, the sum from I equals 1 to n of I squared. 1 squared plus 2 squared up through n squared. We claimed it was this quantity here. All right, let's prove it by math induction. Does it hold for n equals 1? Let's see, then we'd have just, we have 1 squared, just one term, 1 squared. That should equal 1 times 1 plus 1 times 2 times 1 plus 1 over 2. Substitute in, got the 1 and all those parentheses. That simplifies down to 2 times 3 over 6. 6 over 6 equals 1. 1 squared does indeed equal 1. That holds. So the formula holds for n equals 1. Assume the formula holds for n equals k. So I'll go back up here and simply replace n with k. And I want to make sure the formula holds when n equals k plus 1 under this assumption. So add together 1 through k squared plus k plus 1 squared, add in the next term. Let's associate the first k plus this new term. Okay, it'll be the exact same technique. The fact that we're squaring this time, the algebra might be a little more involved, but the technique's the same. I'm still able to squeeze it onto just 2 slides. So we left off with 1 plus 1 squared plus 2 squared up to k squared plus the next term. We had assumed when I add together 1 squared through k squared that we get this formula. The formula holds for n equals k. That's the induction hypothesis. And we get this new term. Common denominator. Okay, let's multiply by 6 over 6. So we can get a common denominator. Let's add things together. Okay, here's the numerator of the first plus the numerator of the second. All right. Now I got some options. I could multiply all this stuff out. It's probably not a good idea because we're going for a formula that involves a product in the numerator. So let's not multiply out until we have to. Here's a k plus 1 in both of these terms. Let's factor a k plus 1 out. Factoring out a k plus 1 leaves you in that first term with k times 2k plus 1, right? Second term will leave you with a 6 and one of the k plus 1s. Okay. I don't see anything to do but multiply out at this stage. So let's distribute the k here, giving us 2k squared plus k. Distribute the 6, giving us 6k plus 6. All right. K plus 6k gives us a 7k. So simply combine those two. Does this factor? I think it does. Try your FOIL backwards. You'll get k plus 2 times 2k plus 3, right? Let's FOIL it forwards. 2k times k is 2k squared, right? 2 times 2k gives 4k plus another 3k. What was that? The inner and the last gives us a total of 4k, 7k, right? And then the products of these last ones is 2 times 3 is 6. So FOIL it, and indeed, that's how that factors. Remember what you're looking for. I want this to be the formula with n replaced with k plus 1. So if we let n equal k plus 1, what do you have? Well, this would be n itself. Let's see. Oops, let me split it up first. So let's take the k plus 1, bring it out there. We'll take that to be n. K plus 2, let's write that as k plus 1 plus 1, which it certainly is. And let's take 2k plus 3 and write it as 2k plus 1 plus 1. So I've rewritten this in a suggestive style. I know this is going to work out. What we did was isolate a bunch of k plus 1s. And now when I substitute n equals k plus 1, this becomes n, this is n plus 1, n plus 1, 2, n plus 1. There you go. Notice the arithmetic checks. This is the formula with n equals k plus 1. Result holds for n equals k plus 1. Holds by math induction for all natural numbers n. So there's a proof concerning sums of squares. And it's the same thing over and over. Let's do one more in detail, and then we'll look at another theorem we've encountered along the way, and maybe speed that one up a little bit. Sums of cubes. Okay. Sum from I equals 1 to n of I cubed. 1 cubed plus 2 cubed up through n cubed. We alleged and had used this when dealing with functions with cubes in them. So probably not a whole lot because the arithmetic got quite involved. But n times n plus 1 over 2, quantity squared is what we had claimed. Let's do it. So we'll check it for n equals 1. That'd give us one term. There's a 1 cubed. Plug in 1 here. We get 1 times 1 plus 1 over 2. And that gets squared. 1 plus 1 plus 1 over 2. That's 2 over 2. That's 1 squared. Yeah, they're both 1. We're good. The formula holds for n equals 1. Assume it holds for n equals k. When I add up the first k natural numbers cubed, we get this quantity here. Added the next one, add the k plus first one, and the formula should hold for that as well. Here's the sum, the proposition, the formula, obtained by adding the next term, the k plus first term. So we get a k plus 1 cubed. Let me associate these first k things as we've done so many times. And what's going to happen? Probably we'll use this induction hypothesis. We'll get a common denominator, we'll factor, and it'll work. And it looks like this one fits on one slide too. I might be worried the algebra is a bit more involved in this. There's some higher powers of the variables involved in this, it looks like, but somewhere in there there's a k to the 4th power. But it looks like the arithmetic works out okay. So here's what we get, having associated the first k terms. Using the induction hypothesis, I know the formula holds for k, so I'll make that substitution. K plus 1 over 2, quantity squared. We're adding the k plus first term. How about we get a common denominator? That'd be 4, right? We've got a 2, but it gets squared. So let's take this as 4 over 4. Let's add the numerators together. Okay, then let's do some of the squaring. This would be k squared times k plus 1 squared over 4, k squared, k plus 1 squared over 4, and add this to that. Okay, so that takes care of the numerators. What you gonna do next? Think this formula is a product of some things, so let's not go nuts multiplying stuff out because we'll just have to factor it later. Well, it's already partially factored. There's a common factor of k plus 1 squared. There's a k plus 1 squared here, and there's a k plus 1 squared contained in this as well. Let's factor that out. And I expect to see some squares. Remember where we think we're going to end up with this. So I expect to see squares in this formula. Factor the k plus 1 squared out. Let's see, that leaves you with a k squared here. There it is. Leaves you with a 4 and one last k plus 1 here. Let's distribute. The 4, it gives us 4k plus 4. Okay. That's a perfect square. That's k plus 2 squared. Let's write that as k plus 2 squared. And well, there you go. That looks pretty good. Everything's squared. And we got a 2 squared in the denominator. Let's take the k plus 2 and write it as k plus 1 plus 1, like we've been doing. And you should know why at this stage. I'm going to let n equal k plus 1. I'm trying to make it look like the formula after this substitution. All right, so writing k plus 2 is k plus 1 associated plus 1. We take the squaring outside for one thing. So let's take the squaring outside. Remember, we're looking for something that looks like this. So take the squaring outside. That leaves us with a k plus 1, a k plus 1 plus 1. If we'll substitute n equals k plus 1, this becomes n, this becomes n plus 1, n plus 1. And that's the formula for n equals k plus 1. So the result holds for k plus 1. That was the k plus first domino falling. Math induction, the formula holds for all n. So that establishes all those formulas we used in 5.2. Maybe I have a little comment still in the notes after we've done that one. Yeah, example A.2.1 and a couple of the exercises we just did, that completes the proof of theorem 5.2b, the sum of powers of natural numbers. So we've made 3 claims in that, and there's the proofs of those 3 parts. Okay, a couple other examples we'll do. We're going to prove theorem 5.2.a. It was algebra for finite sums, fairly lengthy. All right. Claim is the following. The sum from I equals 1 to n of a sub I plus b sub I. You add these sums together. You could add the a's together first and then add the b's together. Not in the least bit surprising. Differences would behave in the same way. Constant multiples can be brought outside of sums. That's just distribution, really. And if we sum up a constant n times, we get n times that constant. So let's go through 4 proofs using induction of this result of these 4 claims. And let's do this one a little bit faster. Okay. Check the formula. Let's do the sum rule, as they called it. First, formula for n equals 1. That would be a1 plus b1 with parentheses around it equals a1 with parentheses around it plus b1 with parentheses around it. Add the a's together first and the b's second. I don't know how to indicate it with anything more than parentheses. That's true by associativity of real numbers if you want all the gory details. Next, suppose the result holds for n equals k. So I just run through this formula and replace all the n's with k's, and they're just the top, the upper bound on the summation. So we get k's on top. We'll take a sum from 1 to k plus 1. That'll give us a sum from 1 to k plus the new term. Here's the new term, as we've been doing. Next, here's where we left off on the previous slide. The induction hypothesis tells us that the sums of the a sub i's plus the b sub i's is the sum of the a sub i's plus the sum of the b sub i's. Holding for, it's a little typo there, this should be k's. Our upper bound was k's on those. So we have upper bounds of k. Here, 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 and here. So I'll fix that in the notes. Should have upper bounds of k. Then we've added the next term, the k plus first term. We can take that, put it over here, take the b sub k, put it with the b's. I'm using associativity and commutativity of the real numbers. If you want to get that in the weeds over the math details, maybe, maybe not. And then we've got a sum from 1 to, when I correct this, 1 to k, and then we've got the k plus first term, a sum from 1 to k, and then we've got the k plus first term. So you ultimately have a sum from 1 to k plus 1. A sum from 1 to k plus 1 of the a sub i's. That is the formula when I substitute for k plus 1 parameter n. So the result holds for n equals k plus 1, and by induction it holds for all n. Not a surprising claim, more an illustration of the principle of mathematical induction. If we were taking differences, guess what? The same thing happens. Let's see if I made the same error on the indices. The sum of a sub I minus b sub I is the sum of the a sub i's minus the sum of the b sub i's. It certainly holds when n equals 1, as did the sum. Suppose it holds for n equals k, giving us this. Let's look at n equals k plus 1. The meaning of that is add together the first k terms and then the new term. Picking up where we left off, yeah, I cut and pasted, and there's those 4 n's that bug me again. Then we have, by the induction hypothesis, that this can be written as a sum from I equals 1 to k of the a sub i's minus a sum from I equals 1 to k of the b sub i's. That's the induction hypothesis. You pick up these new terms. You put the a sub k plus 1 with the a sub i's, the b sub k plus 1 with the b sub i's. So the only thing I could think to get mixed up on is there's a negative sign, right, that's been factored out. So the signs are correct. The ends are wrong, but the signs are correct. And then we've added from 1 to n, a sub I plus the next one, 1 to k plus the next one. So here's a sub 1 through a sub k plus a sub k plus 1. Absorb it in that summation and increase the index. And that's what we're doing in both of those. And that's the formula for n equals k plus 1. Constant multiples. Okay, does it work for n equals 1? Constant multiple times a sub I summed up equals a constant times the sums of the a sub i's. Yeah, this is just distribution. So distribution is usually stated as a hypothesis about the real numbers, an axiom for the real numbers, in terms of a sum of two things. So technically you need an induction proof to establish it. Certainly it holds for n equals 1. Suppose it holds for n equals k, and let's look at k plus 1. I'm going to take a sum from 1 to k plus 1, treat it as a sum from 1 to k, and add that new term. Add that new term. Hypothesis, induction hypothesis says when you have this, you can bring the constant out front. Now I've got a constant times a number plus a constant times another number. I can factor constants out. That's a distribution. We're adding together two numbers. The first one is itself a sum, but we've got a constant times a number plus the same constant times number. Factor the constant out. That is distribution of multiplication over addition, part of the properties of the real numbers. And again, now we've got a sum from I equals 1 to k of a sub I plus an a sub k plus 1. Take that, put it in the sum, and kick the upper bound up by 1, just like we did in the previous. And that's where I had the typos with the ends in the previous ones. So it should read more like this. And this is a sum from I equals 1 to n of a sub I if we set n equal to k plus 1. Formula holds for k plus 1. Formula held for 1. By induction, the formula holds for all natural numbers. And finally, from this bunch of rather unimpressive claims, the sum from I equals 1 to n of c equals n times c. Yeah, not a surprise. C is a constant, so this is c plus c plus c plus c plus c plus c n times. Well, of course you get n times c. Let's establish this one by induction. When n equals 1, it says c equals 1 times c, and that is true. Secondly, suppose it holds for n equals k. Sum from I equals 1 to k of c equals k times c. Wherever I see an n up here, we're putting a k. We get a k over there on the right-hand side this time. And consider the sum from I equals 1 to k plus 1. Let's see. Well, we'll peel the last term off, as we've been doing, or treat it as a new term. They're all constants, so they're always the same. But we get a sum from I equals 1 to k of c plus one more copy of c. Hey, I know what this is. The induction hypothesis says that's k times c. The induction hypothesis says that's k times c. So we got k times c plus c. Let's factor c out, leaving us with a k plus 1. Set n equals to k plus 1. That's n times c, and that's the formula. So the formula holds for n equals k plus 1 by induction, holds for all natural numbers. Induction is very useful stuff to establish some things maybe that aren't quite so clear. This particular exercise contains some fairly unsurprising results. Here's something we stated back in section 3.3, chapter 3, when we had introduced rules of differentiation. And we had glanced at least at exercise 3.3. You're asked to prove a general product rule. So this is something a bit new. It's not stated in the very body of the book. It is stated as a supplemental exercise. Actually, I'm not sure they state it. They hint at it in this exercise. Let's prove it. This is something new. Use an induction. The claim is, if we had differentiable functions, u sub 1 through u sub n, And we wanted to differentiate the product, u1 times u2, blah, 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 times u sub n, a product of n functions. I'm going to put them in parentheses because you probably know where I'm going with that. The derivative of the product of those n things is given by that stuff on the right. So what we have here is a product of all of those functions with the first one differentiated, plus a product of all of those functions with the second one differentiated and the others not, plus a product of all those functions but with the third one differentiated, etc. Till we get down to the second to the last step. We get the product of all those functions except the second to the last one is differentiated, plus the product of all those functions except the last one's differentiated. So what you see is I simply take these functions, write them out, there's n of them, write them out n times, add together, differentiate the first function in the first product, differentiate the second function in the second product, third function in the third product, and continue to work your way diagonally down till you get to the last function in the last product. That's the pattern with a regular old product rule, except there's only two functions. I mean, I can isolate it if I could just pick out the u1, u2, u1, u2, well, u1 prime, u2 plus u1, u2 prime. These four little pieces there, if all the other stuff wasn't there, that'd just be the regular old product rule for two functions. So we're taking the regular product rule for two functions and that pattern it has and easily illustrated with my square brackets. It follows for products of any number of functions. To prove this, I need to introduce a little bit of new notation. This, if it's in that calculus book, it's kind of hidden. It's probably in some exercise somewhere along the way. But just as we have a summation notation based on sigmas, sigma for S for sum, there's a product notation based on pi's. Well, pi's for P for product. So it's a product notation as well. And we could write the product of U1 through U sub n as a product from I equals 1 to n of U sub I. Okay, so it's just like the summation formula, except instead of summing, you multiply. Then we can express that alleged theorem, express that claim as the derivative of the product is, remember it was a sum of n things? In the first sum, this would be j equals 1. We had the derivative of the first, that'd be u sub 1 prime, times the product of the others. This says, let's take a product from I equals 1 to n, except for I equals j of u sub I. So what you're getting here is a product of all of the functions except for the jth one. And that's the one you're differentiating. When j equals 1, we get a u1 prime here. We get a product of u2 through u sub n out of this. When j equals 2, you get a u2 prime here, and you get a u1 times u3 times u4 up to u sub n. It skips over the one that was differentiated. So this summation and product notation together, they represent exactly what we had in that pattern. And it gives kind of a clean way to state it. And it makes proving it a little more accessible by having the product notation. First, let's check the formula for n equals 1. When n equals 1, let's see, we'll have one function, we'll differentiate one function. We need to see if all this summation product stuff actually produces a single function. Yeah, it'd be a sum from j equals 1 to n, taking n to be 1, so we get a 1 up here. Product from 1 to n except for I equals 1. Okay, that means you're not taking the product of anything over here. I equals 1 to 1, but not 1, there's nothing there. So we'll just get u sub 1 prime. Yeah, that simplifies to u sub 1 prime, and indeed the derivative of u sub 1 is u sub 1 prime. It's just notation. Let's look at n equals 2 as well and see that this formula really does give the product rule that you're used to, product of two functions. The derivative of u1 times u2, may be a sum from 1 to 2, j equals 1 to 2, u sub j prime times the product from I equals 1 to 2, except for I equals j, this typo, would produce when j equals 1, we get u sub 1 prime. Over here, we take I equals 1 to 2 except for 1, that's 2, and that'll produce a u sub 2. When j equals 2, you get a u sub 2 prime. Right. And then the sum would include everything except for u sub 2, and producing, in this case, only a u sub 1. And that's the product rule. So this is the product rule that you'd have from regular old Chapter 3 product rule, properties of differentiation. Okay, so I mentioned n equals 2. Again, it's not necessary unless I happen to use it down below, which I think actually we probably will. It's not part of the induction procedure, though, necessarily. All right, so suppose the formula holds for n equals k. Here's the formula. All right, here it is written out with k's as the upper bounds instead of n's. N equals k is what we're assuming. And consider the case n equals k plus 1. All right, that would be the derivative of the product of k plus 1 functions, u sub I equals 1 to k plus 1. And let's treat this product as a product from 1 to k, and then there's a new one over here. In the past, we were usually adding, so we added the next term. Here you're multiplying, so I get it as a multiple. It is the next one in this string that we're multiplying together. Now we've got a derivative of a product of two functions. That's the straight up product rule. Or if you like, it's this thing with n equals 2. So that'd be the derivative of the first. Okay, let's write it symbolically with square brackets and stuff. Be the derivative of the first function, which itself is a product, times the second, u sub k plus 1, plus the first, that weird product, times the derivative of the second, would be u sub k plus 1 prime. Square brackets, round brackets, square brackets, product rule with my square bracket notation. What's the derivative of a product of these k functions? Well, that's the induction hypothesis. We assumed that formula holds. So I can replace this by the induction hypothesis with this stuff here. The formula holds by assumption when n equals k. Product of k things has this as its derivative. The rest of it we're just stuck with. So we get a u sub k plus 1 here, nothing we can do about that, and a derivative over here. Okay, I got my square brackets, round brackets, square brackets, a touch more explicit in this, but that's the induction hypothesis. Here's where we left off on the previous slide. So we've used the induction hypothesis. Now we need to paste these things together somehow, doing some factoring or something. How about this? Here we've got a product from 1 to k of u sub I. And we're going to multiply all those by u sub k plus 1. Well, then we can just replace this product from 1 to k as a product from 1 to k plus 1 and absorb that in the product. We've done some things like this with summations. We're still avoiding I equals j, so this absorbs that u sub k plus 1 into this summation. So it gets absorbed here. The index went up by 1 to take care of the u sub k plus 1. Over here, let's bring the u sub k plus 1 prime. Let's write it on the left instead of the right. I got my reason. So we have derivatives on the left. And let's take this product from I equals 1 to k of u sub I, and let's write it as a sum from I equals 1 to k plus 1 of u sub I. But I is not equal to k plus 1. All right, so what I did is I increased the upper bound by 1, and then I threw it out. So you can't argue with the equality of it. I really didn't do anything. But I'm changing the notation. Hey, look at this. This stuff here looks exactly like this stuff within the summation, except here we've got a sub j, and we've got an I is not equal to j. Here we've got a sub k plus 1 and an I not equal to k plus 1. Everything else is identical. You got the primes here, you got the u sub i's here, you got the upper bounds are the same. So everything within this summation, not the summation itself, this looks exactly like this. In fact, if you were to, you don't do it in this sum, but if you were to let j be k plus 1 here, you'd get this. Okay, well then let's take this, throw it into that sum, up the upper bound by 1 to k plus 1, and when j equals k plus 1, the top of the upper bound in this summation, that'll produce exactly this new term. So we've taken this term and absorbed it into the summation. we've done that before in these previous induction steps. It's just a touch more weird here because of the products and the summation notations, but we've absorbed terms and sums before. It's that idea again. It's just a little more clunky because of all the subscripts and stuff. And if I'll let n equal k plus 1, we get these upper bounds to be n, and that's exactly the formula we had. So the formula holds for n equals k plus 1. By math induction, it holds for all natural numbers n. So that last one, there's just something a touch more involved than some of these slightly more elementary things. And again, I don't think that's quite in the book. They never explicitly state that, and they avoid the product notation. Maybe that's why they never state it. But that takes care of this supplement or this appendix, which I would treat as a supplement to section 5.2 because those formulas were predominantly used in section 5.2. So have a nice day. Hopefully I'll see you back in chapter 5. And the time to do this would be probably after 5.2 and before we get into 5.3. Have a nice day. I'll check you later.